Hi, my name is Brandon Gracely. I'm a high school math teacher. We are going to learn about the relationship between the graphs and the equations of polynomial functions. So first, let's remember the factored form for quadratics. It looked like this. Y equals a times x minus r, you may have used a different letter, and x minus s. You may have used p and q or something like that. And these two values, r and s, they are the roots, or we say the zeros, of the polynomial function. So they tell us where the x-intercepts are. That is where y equals 0. So here's the thing. If these values were different, then we get two x-intercepts. The parabola has two x-intercepts. So let me give you an example of an equation like that. Let's say y equals 1/2 times x plus 1 times, let's say, x minus 2. I'll just draw a little sketch of that over here. So these are my x and y axes, and I'll just kind of eyeball this. There's the first root, -1. So x minus -1 gives us x plus 1, and then over here we'll have +2, and this opens upwards, so I'm expecting a graph that looks something like this. Two different x-intercepts. And we would say the following now. This is a bit of new learning. We say that each of these zeros has order 1. So that's a new thing we're going to discuss as we go along here, but essentially each one of these is unique, and we're going to see what happens with larger order numbers as we move forward here. So that's what happens if the values were different. So the alternative then, if these values are the same, the parabola has only one zero. Parabola has only one zero, or we're going to write x-intercept. So let's do a similar equation. How about 1/2 times x plus 1 times x plus 1? You can see there that those are the same thing, or we might even write it in a slightly different form, x plus 1 squared. Little sketch again. So now the roots are -1 and, well, also -1, and so this parabola opens upwards again, just like that. It's in a different place, and it goes through that one spot right there. Sorry, that wasn't a very good parabola, but that is the vertex. The vertex is on the x-axis. It doesn't drop below it at all. It just kind of touches it in one spot, and then it reverses direction and heads upwards. So now this new word that we're working on, we say that this is a zero that has order 2. And in the equation we can see essentially there are two copies of this, or it has the exponent 2. So two copies of the same factor, or the exponent 2 is on the factor there, and that gives us the order. So now you might be wondering what's going to happen as we increase past order 2. So let's draw a little sketch showing this sort of progression as we move order 1, 2, 3, and we're going to go to 4 and 5, and we'll see this pattern start to develop. So all I'm going to do is draw like an x-axis here. I'm not going to draw a y-axis because it doesn't matter. Just call that our x-axis. And then I'm going to show you what happens when a function has a factor like that, a root or a 0 of order 1. And we just saw this happening with a parabola. It kind of swooshed right down through it like that, and it went through in a single point. And it just kind of went straight through from one side to the other, or if you want going this way, from below to above. And that's it. That is what it looks like. Maybe I'll put arrows on the ends of that to show that it continues. And we've also now seen what happens with an order 2, 0. It's going to just touch the axis and then return in the direction it was traveling from before. So it looks like that, touching in one location exactly. Okay, now how do things change when we have an order 3, 0? So I'm going to give an example of one here. I'm going to just draw one. Looks like it's going to turn into the parabola style, but then it changes its mind and it shows kind of the other half of that parabola style going the other direction. So it curves in like it's going to bounce off, but it doesn't then. It crosses at the last moment and then continues. And that's called a point of inflection, but you don't need to remember that right now. And what about order 4? And this is where we'll start to really see the pattern developing. I'm hoping that you might be able to see it already. An order 4 looks like this. You say, wow, that looks really similar to order 2. And it does. It's very much the same, except it comes in sort of shallower or flatter. It's the same as order 2, but it's been flattened out more. It's more extreme, or it's closer to coming in. There's sort of less of a gap there if the scale is otherwise the same. Here's what order 5 looks like. Comes in really flat again. So look, order 3 and 5 are like the same kind of thing, except order 5 is flattened out more. That's the same with order 2 and order 4. And you know what will happen with order 6? This will be the last one that we draw. You have a prediction? It's even more flattened out. It still only touches in one spot. It's still curvy. It's flatter, but it's not perfectly flat. It does touch in a single location though. So look at 2, 4, 6. It just kind of gets a little bit sharper corners here. It comes in more vertically and then more horizontally. Still curvy though. So that's what the different orders look like graphically. Alright, let's look at some sketches of some polynomial functions. I'll just write a function down and then we're going to analyze the equation using this idea of the order of the zeros, and then we'll draw a little sketch of it. It's not going to be super accurate, but it'll tell us what the shape looks like basically. So I'm just going to use a y equals style here. Here I'm just going to do 1/4 times x minus 2 times x minus 1 times x plus 1. Alright, so let's take a look here. Each of these factors is different, and each of them occurs only once, and they have no exponent, or you might say they have the exponent 1. X minus 2 has order 1, this has order 1, this has order 1. So let's maybe make some notes here first of all. What is the overall degree? Well, this is in nice factored form, so this has degree 1, 2, 3. There are 3 x's multiplied together. No exponents to worry about. So this has degree 3. That means it's a cubic function. That's of odd degree, so that's going to matter in a moment. What is the leading coefficient? Well, this is not in standard form, but you can still see the coefficient. the leading coefficient is this number out here, 1/4, and it's positive, because everything here is just an x in each of these factors. If there was like a 2x in here, you'd have to factor out the 2 first before you could see the leading coefficient of 1/4. Okay, so this is an odd degree function that opens in the usual way, sort of goes from, so maybe I'll just list the end behavior here. The end behavior, it kind of starts in quadrant 3 in the bottom left, and it goes up to quadrant 1 in the top right. That's the end behavior. Now we have to see what happens in the middle. I'm going to draw a little sketch now. Let's see, my roots are going to be 2, 1, and -1, so I can just maybe draw the center right here, the y-axis here. So over here I needed a -1, I need a +1, and a +2. That looks alright. So those are the places where the curve is going to either cross or touch the x-axis, and that will depend on the order of the roots. Well, these zeros all have order 1, so I'm just going to go back to the sketch we did earlier. Order 1 means it just crosses right through. We're starting in quadrant 3, the bottom left. So we're going to go up through this one. I'm going to just kind of put a little mark through there. Then we have to come back down through this one, and then we're going to go up through this one. So now I'm just going to connect these with kind of smoother curves. And that's it. Each of those is order 1, so they're smooth crossings like we drew in that earlier pink graph a moment ago. Smooth crossings, 1, 2, 3 of them. We started in the bottom left, we ended in the top right. That's because of the degree of the polynomial function, degree 3, and the leading coefficient is positive, so that's why we started in quadrant 3 and ended in quadrant 1. Okay, let's try a second example. That's number 1. How about y equals 4 times x minus 2 squared times x plus 3. So a little bit different this time. Let's check out the degree again. Well, we have 2 of these, so there's going to be 2 x's multiplied together here, one of them here, because there's only an exponent of 1, so that's again a total degree of 3. If you're not sure about that, go ahead and multiply this all out, and you'll find when you get to standard form that you do have a degree 3 polynomial. The leading coefficient is 4 in this case, right there. That's a positive number. So once again, we're going to have the same end behavior. We're going to start in the bottom left and end in the top right, starting in quadrant 3 and ending in quadrant 1. Alright, but this graph will look a little bit different. Let's start sketching it out. Let's see, I've got roots are positive 2 and negative 3. So maybe I'll move this over just a little bit. Positive 2, negative, that looks like about negative 3 right there. Now I know that this one is an order 2, 0. Positive 2 is an order 2, 0. Order 2 looks like that. That's a bounce. So this one is going to have to bounce off of there. It's going to look like a parabola, and it has to extend up towards positive infinity at the end after that 0. There's no other way for it to go. So it has to go up there, and it has to bounce. So it's going to come in like this. Now on this side, the other 0 at negative 3 has to get is an order 1, 0, so it's going to be a smooth crossing, and because this curve is already up here, it's got to come down this way. And I also know that it has to come down this way because it has to get down to quadrant 3, moving towards infinity. So it's going to look something like that. Now it may not go up that high, it might be flatter than that, but this gives us the idea of what the curve looks like. It's a regular cubic curve, it's the usual style, but it goes through these points. Negative 3, and it just barely touches at positive 2. Alright, let's do one more. Y equals negative 2. Let's have x plus 1 cubed and x minus 2. Okay, degree 1, 2, 3, 4. You can just count the exponents up if it's in this nice form. Degree is 4. Leading coefficient, everything's nice in here, and so we have -2. We have a -1, that's nice. And so that means the end behavior, well, degree 4 would go top left to top right, except it's been flipped over. So it's bottom left to bottom right. Okay, let's try drawing this sketch out. So we need zeros at -1 and +2. So I don't need a real big graph for that. -1, +2. Okay, so let's start off with the 0 at -1. It's of order 3. That means it's going to look like that. Maybe flip the other way, we'll have to look, but it's going to have, it'll curve in towards that 0, and then it continues on through with the same curve. Now we're starting in quadrant 3 to get there, so we're going to have to do exactly that shape. Curving in, and then continuing on up afterwards. So it doesn't come through on a straight line the way an order 1 does, it has a curve to it. And this last one at +2 has to go straight through so that we can descend down into quadrant 4. So this curve is going to go up and then down, down this way. It doesn't flare out like that. And I kind of missed my mark there, but it comes down and then it continues sort of accelerating downwards. Not my best curve, okay, but you can pretend that I did that correctly. So this one though, that's an order 3, so it comes in on a curve and it leaves on a curve. It's changing direction there a little bit. Okay, let's take a look at this polynomial function that's been graphed here already. And I have 1, 2, 3, 4, I have 5 zeros, and I'm wondering what could the orders of these zeros possibly be. So let me just label them down here. And then let's consider each of them. So there's 0a. We go from below the x-axis straight through it and then continue up. And because it's in a straight line here, and there's no curve or wobble to it at the 0, that must be of order 1. When I come in at b here, it looks quite flat. In fact, I notice it's flatter than this one over here. So I would expect that maybe that's an order 4, but it's definitely an order 2 or 4 or 6 or one of those. It has to be an even order like that. It might be 2, it just depends on the scale of our graph. It's hard to know. So what we would say is it's at least 2, and it is definitely even. Coming in at C here, we have a curve coming in, and then it continues and curves down across the x-axis. That makes this an odd one, and it's not like A, it's not order 1. It has to be at least order 3 because of that curve. So it's order 3, but it could be order 5 or 7 or so on. It's one of those. D, we have that bounce thing happening again, so that's got to be order 2, or it could be 4 or 6, something like that. It's at least 2. And E looks like a nice smooth straight curve through there, different from C. Straight curve just like the one we had at A, so that is an order 1. So you're essentially getting a 1, or 2 or another even number, or 3 or another odd number. Those are the different options you can have for zeros. And as I said, the straighter in it comes like this, B compared to D, the more likely it is to be a higher order like 4 or 6. Often when we are talking about functions, we need to discuss a special region or interval on the graph, and so we have a special notation that goes with it. I know we always make up new notations in math, but this one actually makes things a lot easier, a lot shorter, and it's not that difficult to learn. So let's write a little definition first. So an interval is a continuous region such as, I'm going to give an example, such as the region from, let's say, x equals 2 to x equals 4. And one of the things that we're going to have to deal with is, do I mean 2 to 4 and everything in between, or do I mean just the parts in between 2 and 4, not including those, Or do I include 2 but not include 4? And so we're going to have to be careful in our language, but that's one of the things that our notation will do for us. It will help us to clear up, do we mean to include those endpoints? So we can use words, or we can use number lines or interval notation, and we can even use that set builder notation like we use for domain and range. So let's look at a few examples. Let's say we are talking about the interval from 2, and I'll say maybe from x equals 2 to x equals 4, including 2, but not including or excluding 4. So I don't want to include the value 4, but I do want to include 2. So maybe I'll just start by drawing a number line here. So 1, 2, 3, 4, 5. So you may be familiar with this way of writing intervals, or by making note of them. So I do want to include 2, so we put a colored in dot on 2, all the way colored in. And then I'm going to shade or highlight all the way to 4, but I'm not going to include 4, which means I need to put an open circle at 4. I don't color that circle in, and then we do shade in the line in between. So that's a way to indicate all of the values from 2 up to 4. Now interval notation for that set looks like this. We want to include 2, so we put a square bracket, and then the number 2, then a comma, then the number 4. So those are the 2 end points of the interval. See, it's a continuous region. Now because I don't want to include 4, the symbol we use to close it off is a round bracket. So this says everything from 2 to 4, including 2, but excluding 4. If I had drawn the round bracket over here, it would exclude 2 as well. I wouldn't have 2 as part of my interval. Now a set builder way to write this, which is the way that we often write domain and range sets, you could write something like this. The set of all x values that are real numbers such that 2 is less than or equal to x, which is strictly less than 4. See how I didn't put an equal sign there? Just less than 4. So that's the set builder version. Now can you see why the interval notation tends to be kind of nice? Set builder notation is pretty huge. Interval notation is quite small. And you could put an x element of right in front here if you wish as well. I'll leave it off now to keep that clean. Alright, let's try another one that's maybe a little bit different. I think maybe we just need 2 examples even. Let's say the interval from, let's say, positive 5 and greater, maybe is a good way to describe that with words. I mean positive 5 and any number bigger than positive 5. On a number line, I want to include 5, so I color that in, and then I go this way, and I just follow it along and I include the arrow in my colored in part. So that's how you draw it with a number line. That's no big deal. 5 and everything larger. Notice it colors in like in between the numbers too, so I do mean 5.5 and 6.27 and so on. So interval notation looks like this. Well, I do want to include 5, so I'm going to put a square bracket, not a round bracket this time. 5, comma. Now normally I would put an endpoint. So in the last one we had 4 as an endpoint, but here there is no endpoint. It goes forever. And so we do indicate that with positive infinity. Now positive infinity is not an endpoint. It's not a single location that I can stop at. So I can't put a square bracket there because it's not really a closed interval like that. So instead I put the round bracket to indicate that I sort of don't include the endpoint because it's not really a point. So once again, we have a square bracket to indicate that the endpoint is included, a round bracket when it's not included, and we always use a round bracket with infinity. And one last thing I want to mention is if we go to the other end and we have negative infinity, it would come first, negative infinity on the left with a round bracket, and then some larger number on the right. Always, the smaller number is first. So here, 5 is on the left on the number line, and infinity is on the right, and it stays that way with interval notation. 2 is on the left, and 4 is on the right, and it has to stay that way. You can't put 4, 2 with interval notation. Also, one other quick point, if you have an open interval on both ends, like it doesn't include 2 and it doesn't include 4, you'll have round bracket 2, 4 round bracket, and it will look like a point, like an ordered pair like you're used to using for plotting on graphs. So be careful that you don't get confused between interval notation and points. Well, interval notation gives us a nice way to talk about the sign of a function, positive or negative, over the intervals. It gives us a concise way to write that down. So let's look at a specific example here to explain this idea. Let's go with -3 x minus 3 squared x plus 2 cubed and x minus 1. Now this function has 1, 2, 3 different zeros. One of them has order 2, one has order 3, and the last one here just has order 1. I'm also going to note that it has degree 6. 1, 2, 3, 4, 5, 6. The leading coefficient is, yep, those are all factored, so that is -3, that's the right leading coefficient. And that means the end behavior, let's see, it's an even degree, so normally it opens up, up. Sorry, it goes to the top on each side, the first and second quadrants. But this has a negative leading coefficient, so that flips the whole thing over, and this will go from quadrant 3 to quadrant 4 into both of the lower quadrants. Alright, and we've already looked at the order of the zeros. Maybe I'll do a little wee sketch just down here, just to make sure that I have my brain around this. Let's see, that's a +3. That's a -2. And that's a +1. Okay, so those are the zeros. I know that it has to start down here. It has to end over here. Let's figure out what happens in the middle. Well, when we come up on this 0, the -2, 0, it has order 3. So it's going to come up from below and do that squiggle, but it will cross, which means it does change sign. So down here, the graph is negative, but once it goes through this spot, it's going to change sign from negative to positive. And we'll see that in our chart that we're going to make in just a moment. When we get to the next 0, which is +1 right here, it has order 1, which means it's going to go swoosh right through. And so it's going to do that straight through. Let me just connect up my little sketch here. Goes straight through, no wiggles like that. And then last we have the +3, 0, which has order 2. That's a bounce. That's good because I need to go down here, and so now I can just connect these up. And that's what our graph essentially looks like. Comes from down here, ends up down there, and this is how it wiggles and bounces in the middle. Alright, now let's make a little chart that describes those changes, or rather describes the sign of each interval. So we have an interval here, we have a second interval there, third interval, and a fourth interval. And the thing that divides these intervals up are the zeros. See, that 0 right there puts the graph into two pieces, the piece on the left of it and the piece on the right of it. Over here it's negative, over here it's positive. So here's what our chart will look like. It's going to be kind of a sideways chart, interval on the top, sign on the bottom. You could do this the other way as well, but it's I think it's more intuitive to see it this way. So the first interval is everything from the left all the way up to -2, not including -2. So that's negative infinity on the left, so that's the x value, all the way up to -2, but let's not include that because at -2 that is an x-intercept. We know the value of the function there is 0, so it's not really meaningful to talk about a positive or negative sign there. So that in that region, or in that interval, the function is negative. And then on the other side of that 0, we're going to go from -2 to +1. And once again, round bracket to say, let's not talk about -2 exactly, just everything beside it, up to +1. And in that region, in that interval, we are above the x-axis, so the function is positive up here. We continue from 1 to the next 0, which is at 3. In that interval, the function is negative. And last we go from 3 to, well, there are no more zeros, so we continue to positive infinity. Positive infinity is the x value. We're not worried about the y values there. The sign, that's where we'll see the y values. Those are all negative y values. Okay, so let's check this out. We started off negative, and then we came across a 0 of order 3. That's an odd number, and we changed from negative to positive. Then we get to the next 0. That's of order 1. We change again, positive to negative. Then we come across the last 0, which was x equals 3. That is a 0 of order 2, an even number. And look, we didn't change sign. We were negative, and it just bounced, and we stayed negative. So when we have an odd order 0, we change sign, negative to positive or positive to negative. But when we have an even order 0, the sign stays the same. It stays positive or it stays negative because there is a bounce. Okay, let's take a moment to remember the standard form for any polynomial. We would have a function name maybe, but y equals, we have the leading coefficient a sub n times x to the exponent n, and n is the degree of this polynomial. So that is so far a power function, but for the more general form, a sub n minus 1, x to the n minus 1, and so on, down to the last couple, a sub 1x, you could put the exponent 1 there if you want, plus a sub 0. So I want you to remember that, and now I'm going to give you a new definition that's not just about polynomials, it's about functions in general. So two definitions actually. The first one is this: a function of any type is even, not of even degree, just even, if it is symmetric about the line x equals 0, which is the y-axis. So if you reflect the function in the y-axis, it won't change it. It looks exactly the same. So that might sound familiar because we've seen something like that recently. And the second definition is this: a function is odd, not of odd degree, just odd, if it is symmetric about the point 0, 0. Which is the origin. Okay, now we did just see both of those. This happened when we had an even degree power function, and this happened when we had an odd degree power function. But these definitions are both going to apply to other kinds of functions, including other polynomials that are not power functions. So here's how we're going to know. So a polynomial function is even if every term of the function, every term, has even degree. And that includes the last term, which is the constant term. So it can have a constant, but for example, it can't have a linear term like this, like 2x, can't exist in the polynomial if it's going to be an even polynomial function. So every term has to have even degree for the polynomial function to be an even function and to have that symmetry. And I bet you can guess what's coming now. A polynomial function is odd if every term of the function, when you write it in standard form, has odd degree. And what you'll notice then is that it can't have a constant term because that has degree 0, but it can have, for example, that linear term, but it couldn't have like a squared term or a term with degree 4, and so on. So these already happen sort of by default with power functions, because a power function like 5x squared has only one term and it's even, so the polynomial function then is an even function. So power functions get these really cheaply. Other polynomial functions, you have to check every single term to see if it works. So you might be wondering, what happens if we don't have every term with even degree or every term with odd, but there's some kind of a mix? And the answer is that we don't get the symmetry then. There is no symmetry or no nice symmetry like these ones if you have a different kind of polynomial. So these special symmetries only occur when you have all even terms or all odd degree terms. Let's maybe just practice a little bit. Write down a couple of examples here, and then you can test these out by graphing them yourself to see how they look. So let's identify whether each of these is even or odd or neither, and let's give some reason for each one. So here, let's start with, let's start using function notation. F of x equals 4x squared minus 3. Now you might be familiar with this because it's a parabola, but let's just look at the degrees of each term. So this term has degree 0. I'll write it underneath here. That's a degree 0. 0 is an even number, and that's degree 2. So these are both even degree. So this is an even function, which means it's symmetrical about the y-axis. You could flip it or reflect it across the y-axis, and you'll get exactly the same function. Let's try g of x is, let's see, 9 times x to the 4th minus 4x. Alright, so this term has degree 4, and this term has degree 1. So it's not even because there's a 1, it's not odd because there's a 4, so this one is neither. Let's try another one. H of x is next. Negative 1/2 x to the 5th plus 3x cubed minus x. Okay, degree 5, degree 3, and this one is not listed here because it's degree 1, which means that we here have an odd function. Those are all odd numbers. Let's go a little different here. Let's try j of x, I guess we should do next. 3 times x minus 1 times x plus 2. Now, this is not in standard form, so you can't just look at it and say, oh, well, this is going to have a degree 3 and a degree 1, so it's odd or anything like that. Instead, you have two choices here. You can expand this out, and you will see the standard form version of it, which you can then analyze like we've been doing. But I'm actually going to notice something. This is factored form, so I can read all the zeros. This 0 is 0. This 0 is positive 1. This 0 is negative 2. Now I notice that positive 1 doesn't have a -1 counterpart. So there's something that happens on one side of the graph that's not happening on the other side of the graph. So this one is also neither. So you can use some other reasoning to notice that there is a problem with some graphs and that they're not going to have the symmetry. You can only do that with zeros, by the way. You can't do it with higher points because you'd have to check to see if it matches the opposite corner. Let's do one more here. How about 4 times x minus 2 times x plus 2. Okay, so this one also has some zeros. Let's see. X plus 2, or sorry, this will give a positive 2, 0, and this will give a negative 2, 0. You know what? I think this looks like it could have even degree. It looks like it's got a symmetry. Maybe I'll just expand this one out just to double check. Those two terms cancel out, or rather they add up to 0. Looks to me, oops, let me put this on the screen, 4x squared minus 16. Looks like a degree 2 and a degree 0, so this is an even function. And you might be able to just remember this from looking at it. There's a few other ways that you can reason your way to that place. So we have a few different strategies here, and I've got one more thing in particular that I want to show you. Is that when a function is even and has that symmetry, it has an algebraic way to write it. So we can record this in the following way. F of negative x is equal to f of x for all x in the domain of the function. So what that means is like f of negative 5 is the same as f of 5, or f of 7 is the same as f of negative 7. You can look at one side of the graph and you'll know what's happening on the other side. Now for odd functions, we also have a different algebraic way to record it, and it looks like this. If you take f of negative x, you don't get f of x, you get negative f of x. You get the same thing, but it's been flipped over as well. So it's reflected twice, reflected to the left and reflected down is a good way to think about it. For all x in the domain of f. So we have essentially two good strategies for finding out whether a function is even or odd. If it's in standard form, you can look at the degree of each term, and you can also test individual points. And this is a good way to show that something is not even, is you put in a value like f of negative 5 and f of 5, and you check to see if they are the same. If you ever find a pair that don't match, it's not even. Okay, thanks.